Hello, today we are going to start talking about some basic discrete structures that include sets, functions, sequences, sums, and also matrices. We are going to start talking about the set, which is the fundamental discrete structure that the other discrete structures are built on. For example, think about all possible unique combinations for a car license plate. If the license plate has 6 spots and if we can use 26 letters and 10 digits, how many unique license plates can we generate? That's a combination problem, and that's related to unordered listing of the objects or elements of a set. So let's start talking about the set itself. Okay, so this is Comp 3010 Discrete Mathematics class at Tennessee State University. And we are going to start talking about sets today. And next lecture, we're going to talk about functions. And then we'll talk about sequences and sums, and also matrices, which are basic discrete structures. So what's a set? Well, a set is the most fundamental discrete structure, and all other discrete structures are built on the set. And sets are used to group objects. For example, all the students in Comp 3010, which is this class, is a set. Even though sets are typically contain the same type of objects, it is not required. For example, all the students in this class and an apple and an orange together might be a set as well. So the elements of a set do not have to be what? Of the same type. And what are we going to do? We are going to learn the language of sets today. It's a very actually trivial lecture, very simple, very intuitive, but we want to formalize so that you can learn the language of sets so that we can study the sets and other discrete structures in an organized fashion. So what's a set? A set is an unordered collection of distinct objects. Again, a set is an unordered collection of distinct objects. And those objects are called elements or members of the set. For example, lowercase a in capital A, that means this is the set and this is an element of the set. This is the notation to tell us that lowercase a is an element of set A. Here, lowercase a is not an element of set A, okay? Sets are usually denoted using uppercase letters like this one, and elements of the sets like this one are typically denoted using lowercase letters. How do we describe a set? Well, there are different ways to describe a set. Roster method, set builder notation, or interval notation. We're going to see those 3 methods. In the roster method, it's very simple. We describe a set by listing its elements, basically. In the set builder notation, this is the notation that will describe a set by stating a property that all elements of the set must have in common, okay? And then we'll talk about interval notation later. Here is the roster method examples. For example, the set V of all vowels in the English alphabet can be written as A, E, I, O, U. So V is a set that includes 5 elements in it. Another one is O, the set O of odd positive integers less than 10. For example, how many odd integers do we have less than 10? 1, 3, 5, 7, and 9. O is a set that contains 5 elements. So we are listing all the elements. That's the roster method. Okay, although a set's elements are typically of the same type, but they don't have to. For example, here the set A, 2, Fred, New Jersey is a set that includes 1, 2, 3, and 4 elements of different types. Another example, the set of positive integers less than 100. Well, of course, we cannot list all 100 of them, but we can say 1, 2, 3, and then ellipses like dot, 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 99. That means it is 1, 2, 3, 4, 5, 6, and all the way to what? 99. Set builder notation is also very intuitive. Then we are going to specify a property or properties that all members must have. For example, here I say S is a set that consists of X, which elements, we call them X, such that X is positive integer less than 100. Okay, so S is a set that then each element is a set of elements x, and x is a positive integer less than 100. Or I can say O is a set, consists of elements, and each one is an odd positive integer less than 10, okay? Or here, x is a positive integer, and x is odd, and x is less than 10. So all of them means what? For example, here S, that means it's a positive integer less than, it's a positive integer, so it starts with 1, 2, all the way to what? 99, because strictly less than what? 100. Or O is, what does it say? An odd positive integer. So first of all, positive integer, and it's an odd. So 1, 3, 5, 7, and 9, because strictly less than 10. Or here, O can be also represented just like that. Z plus means positive integers. So O consists of elements of positive integers such that elements are odd and elements are less than 10. So this is exactly the same as what? This one, okay? Or you can use a predicate actually. For example, here you can say set S consists of elements such that Px is true. For example, I can say if my predicate is prime x, in other words, prime x is a propositional function, it says x is a prime integer, then it consists of all prime numbers. For example, what? 2, 3, x is a positive prime number, let's say 5, 7, 11, and so on. Okay, so that's the set of all prime numbers. And positive rational numbers, by the way, this is the set of positive rational numbers such that x is a real number, such that x can be represented as p over q for some positive integers p and q. So that's the set builder notation, okay? For example, here, 3 over 5 is an element of what? Positive rational numbers, because I can represent 3, it is a real number, and it can be represented as p over q for 2 integers, p and q. Okay, some important sets, you need to get familiar with those. Natural numbers, these are integers that start from 0. These are positive integer numbers that also includes 0. And z, which is the integers, the set of all integers from negative infinity to all the positive infinity. Positive integers starts with 1, 2, and then goes all the way to infinity. And R is the set of real numbers. R plus is the set of positive real numbers. Of course, if z plus is positive integers, z minus is what? Negative integers, the set of negative integers. Or we can have like this, the set of negative real numbers, okay? And C is the set of complex numbers. Some of you may not know what a complex number is, but you know, that's represent the set of complex numbers. And then we have Q. Q is the set of rational numbers, okay? And this is the third one, interval notation. Well, the first one was roster method. The second one was set builder notation and interval notation. This is for real numbers. I mean, you're already familiar with that. For example, AB represent the interval. AB represents all the elements of real numbers such that it is between A and B inclusive. So for example, here, if this is 3, this is 5, this is what? All the real numbers between 3 and 5. So 3, 5 represents all x such that what? X is bigger than or equal to 3 and x is less than or equal to what? 5, okay? And similarly, this is open this is open interval, okay? So for example, here, this one was 3 and 5 inclusive of 3 and 5. Here, 3 is included, 5 is excluded. Here, 3 is excluded and 5 is included. Here, both of them are what? Excluded. By the way, this is a closed interval and this is an open interval. and this is neither closed nor open, okay? Okay, so that's what it is. Well, sets can have other sets as members. For example, here, this is, let's say that this is our set A. A contains 3 members. This is first member, this is second member, and this is the third member, okay? So 2 of the elements of A are set by themselves. For example, 1, 2, 3, this is a set, this is another set. How many elements does the set A have? It has 3 elements. Here 1, here is 2, here is 2. That means sets can have other sets as members. Another example is, for example, you can have a set, let's call it V. V is a set that consists of 4 elements, and each element is a set by itself. Natural numbers, integers, rational numbers, and real numbers, okay? Empty set. Well, empty set is a special set that has no elements. Well, let me give you an example. Assume V is X such that they are positive from positive integers with X bigger than X squared. Do we have any positive integer, okay, who is bigger than its square? Well, for example, positive integers are, we know that 1, 2, 3, and so on. For example, for 1 bigger than 1, is that true? That's false. How about 2? Is 2 bigger than 4? That's false. 3, is that 3 bigger than 9? That's false, okay? So you cannot find any positive integer which is bigger than its square. That means V is an empty set. And this is the notation that we use, okay? Or sometimes we can use left and right braces just like that, okay? By the way, an empty set is also called null set. And we denote it with this or with that, as I express. And this is the example I just gave to you. Okay, singleton set. A singleton set is a set with only one element. For example, this is singleton set, and this is a singleton set. Look, empty. Let's say that this is A. This is not the same as empty set. A is not an empty set. A is a set that contains empty set as an element, okay? So these two are not the same. Here, this is empty set, but here A is a set that contains empty set as an element. For example, A, the number of elements or cardinality, as we will see soon, is 1 for this, but the cardinality of empty set is 0. Empty set does not contain any elements, but this set contains what? 1 element. And if a set contains only 1 element, that's singleton set. Universal set. Well, get familiar with that. Universal set depends on the context that you use. For example, if you have a set V, which consists of all vowels, and if you are dealing with all letters in the alphabet, that your universal set U will be, all letters in the alphabet. So A, B, C, all those 26 letters, okay? So it depends. For example, if you are dealing with integers, then your universal set will be what? Set of integers. If you are dealing with real numbers, maybe your universal set will be set of real numbers. So it will depend on the context, or basically it is the set that contains all objects under consideration, okay? So here U is the set of all letters in the alphabet, and then V is the set of vowels. How about equality? Well, if you have 2 sets, they are equal if and only if they have the same elements. For example, if A and B are sets, A and B are equal if and only if for every X, if X is in A, then X is in B. Or if X is in B, then X is in A. Remember, this is biconditional. That means this direction and this direction, okay? That means X is in A if and only if X is also in B. Okay? So that's what it is, very simple. Well, for example, here, I told you that the set is unordered elements. The set is collection of unordered elements. So 1, 3, 5, 3, 5, 1 are exactly the same. Okay, order is not important. And if you have 1, 5, 5, 5, doesn't matter how many times you have an element, it is the same as having only once. Okay, so because we are talking about distinct elements, so 5, 5, 5 are not distinct, they are the same. 3 and 3 are not distinct. So distinct unordered elements. So here, this set and this set are equal, this set and this set are equal. Sometimes if you want to distinct, if you want to specify that 5, 5, 5 are should be considered separately, then we use multiset concept, but I'm not going to get into that. So what's a subset? Well, the subset A, okay, the subset. For example, let's think about a set A, 1, 2, 3, 4, okay? And then consider B, for example, 2 and 3. We say B is a subset of A, okay? Because any element of B, for example here, 2, is also an element of what? A. And then 3 is also an element of A. So if you pick a random element in B, if that element is also in A, that means B is a subset of what? A, okay? So that's basically very simple. We say the set A is a subset of B if and only if every element of A is also an element of B, okay? And we use this symbol to represent that A is a subset of B. For example, here, it means that every X, for any X, if X is in A, then X is in B is true. That proposition, P implies Q, is true, okay? So my question is, think about empty set, okay? Think about empty set, okay? Let's look at this. For every X in empty set, does it imply that X is in B? Okay. Well, empty set does not contain any element, right? That means this is false. Since premise is false, no matter what Q is, we know that P implies Q is true, right? So in other words, empty set is a subset of any other set. We can always say empty set is a subset of B in this case, okay? So empty set is a subset of any other set. How about, let's consider this. Let's say that we have a set A. How about this statement? Every X in A implies X in A. Let's see. Is this true? For example, if X is in A, which is true, this must be true, and true implies true is what? True. If XA is false, then this is false, and false implies false is also what? True, right? So that means a set is a subset of itself, always. That's what I say here. So empty set is a subset of any other sets, and we know that a set is a subset of itself, okay? All right. For example, think about this. A is equal to 1, 2, 3, right? So if we randomly pick an element like 1 is in A, but also 1 is in A. In other words, A is a subset of what? A. But sometimes for a proper subset, okay, we will see a little bit later, if I say A is less than B, sorry, A is included in B without this, that means A is a proper subset of B. For example, here, if I have A, 1, 2, 3, 4, and if I have B, 2, 3, B is a proper subset of what? A, because B is strictly included in A, and A has an element which is not in B. We will talk about this in a couple of slides later. Well, okay, so how do I show that A is a subset of B? If an element belongs to A, then it also must belong to what? B. How do you show that A is not a subset of B. If you can find one element in A, which is not an element of B, then you're done. For example, here, if I have A, 1, 2, 3, and if B is equal to 2, 6, well, I take 2, 2 is in A. But however, if I take 6, see, 6 is in B. Well, the notation is different. Let's use the same notation, A and B here. I'm going to say B is A, B, C, let's say, and A is B and D, okay? Now, if you can find an element which is in A, in this case, look here, D. D is in A, right? But D is not in B. So therefore, A is not a subset of what? B, okay? It's pretty simple. Okay, here is a simple example. The set of all computer science majors in our school at TSU is a subset of all students at TSU. T, all, or I can tell it like this. T consists of all elements such that X is a TSU student. And then C might be X such that X is a CS major. Okay. If you take any CS major, you know that he is also a TSU student. Therefore, C is a subset of what? T. How about this one? The set of integers with squares less than 100. Well, think about this. A, the set of integers whose squares is less than 100. Well, for example, what are they? For example, if I get 1, 2, 3, 4, 5, 6, 7, 8, 9. Square of 9 is 81, 64, 49, and so on, but I cannot include 10, right? And then also I can go with 0, -1, all the way to what? -9. So this is the set whose squares are less than 100. And think about Z positive integers, okay? Well, is A a subset of Z? That's what I'm asking. It is not. Why? Because, for example, -1. -1 is in A, but -1 is not a positive integer. So therefore, A is not a subset of what? B. Okay. So this is, well, look here. A and B are equal means for any element from the universal set, if that element belongs to A, X belongs to A if and only if X belongs to B, okay? In other words, if X is an element of A, then X is an element of B, or this is this direction, or in that direction, if X is an element of B, then X is an element of what? A. So that means, but when you look at here, what does it say? This says A is a subset of B, and here, when you look here, this says B is a subset of A. A equal B, right? If and only if A is in B and B is in A, okay? So that's what it is. Proper subset, if A is a subset of B, but A is not equal to B, then we say A is a proper subset of what? B, as I was trying to explain. In other words, for all elements in the universal set, okay, here, if that element is an element of set A, then that's an element of set B, okay? So this tells us A is a subset of B. However, there is an element, at least one element, which is in B, but which is not in A, okay? Which is in B, but which is not in A. In other words, if this is set B, this is set A, and these are the elements of A, that means there's at least one element of B which is not in A. Okay, so that is the proper subset of what? B. That's how you show it. This is the universal set. This is B, and this is A. What is the size of a set? We call it cardinality, by the way. That is the number of distinct elements, basically. The number of distinct elements. And if you can count them, and if it's a non-positive integer, then we say S is a finite set. For example, here, 1, 2, 3. This is a finite set, and whose size is what? 3. How about Z plus? 1, 2, 3, all the way to infinity. So this is the size of positive integers is infinite, therefore, basically infinite. There are infinitely many positive integers. So the size of positive integers, the set of positive integers is what? Infinite. And the cardinality of a set is denoted by like that, absolute value of A or A between double pipes. This shows the number of distinct elements, okay? For example, what is the size of or cardinality of empty set? Empty set does not contain any elements, so that means the size is 0. Well, how about if we have set of letters of the English alphabet? How many letters we have? 26, so the size is 26. How about this one? This is 1, 2, 3, the size is 3. And here, remember, this is the set that contains empty set in it. That means the size is 1. Okay, the set of integers is infinite, obviously. So power sets. Power sets are very useful because there are many problems in computer science that will involve testing all combinations of elements of a set. Okay. For example, if I have this, let's say A is A, B, C. Well, maybe I want to get only first element A, or second element B, or third element C, or I want to take AB, okay, and I want to get maybe AC, and maybe I want to get ABC, oh, sorry, A here. Maybe I want to get BC, or maybe I want to get all of it, A, B, C, or maybe I don't want to get any one of them. Basically like this. So the list, I mean, basically this is the power set. Power set of A consists of what? All possible combinations. Empty set, A, B, C, A, B, A, C, B, C, or all of it. Okay. Let's see. This is what it is. We may build a new set. So that new set, we call it power set, considers all combinations of elements of a set S. Okay, here. Given a set S, the power set is denoted by P of S, okay? And it is the set of all subsets of S, all possible subsets. Here you go. What is the power set of set 1, 0, 1, 2? Here it is, power set of this set. For example, if I call S as 0, 1, 2, the power set S is equal to, okay? First of all, it might be empty set, and then it may get the first element, it may get second element, it may get third element, it may get the first two, it may get the first and third, and then it may be second and third, okay? 0, 2, nope, not like that. Okay, and it may get second and third, and it may get all of it, 0, 1, 2. In other words, power set might be empty set, itself, and all those combinations, okay? Okay, what is the power set of empty set? That's a good question. These are empty set. What's the power set? Power set consists of all possible combinations, including empty set. So this is it. Basically, power set of empty set is a set that has only one element, which is the empty set itself. Okay. How about if we have set A, and A is this one? Recall that this is not the same as empty set. This is a set that contains empty set in it. So what's the power set of A? First, it will have the empty set, and it will have everything, the whole A. That means empty set and the set of empty set, okay? A set that contains empty set. What's a tuple? Well, an ordered tuple, I mean, for example, if I say, let's say 1A, and like this. This is an ordered pair, okay? Or ordered two tuple. Or if I say, for example, 1, 2, 5, that is an ordered three tuple, or okay? This is the first element, this is the second element, and all the way this is the nth element. And two tuples can be equal if and only if the corresponding elements are exactly the same. And specifically, two tuples are called what? Ordered pairs. For example, AB is an ordered pair, CD is an ordered pair. If AB and CD are equal, they can be equal if and only if what? If A is equal to C, B is equal to D. So what's the Cartesian product? When you have two sets A and B, the Cartesian product of A and B is denoted by A cross B, and it is the set of all ordered pairs A, comma B, and A will come from first set, B will come from the second set, okay? In other words, Cartesian product of A and B are ordered pairs A and B. The first element comes from first set, and second element comes from what? Second set. Here's an example. What is the Cartesian product of A and B? That's very easy. So basically, I will get 1A, that is one ordered pair, and then maybe 1B, that's another ordered pair, 1C is another ordered pair. The first one comes from A, second comes from B, and then 2A, 2B, and 2C. That is what? A cross B, okay? For example, this one is not, if I say A1, that is not in A cross B, okay? Because this is not an element of A, and this is not an element of B. All right. Well, if you have more than two sets, the Cartesian product will be what? An n tuples, and each element will come from the corresponding set. Okay, for example, here, A is this, B is this, C is this, A cross B cross C. Well, I guess we can do this way. We have 0 here and 1 here, right? This is for set A. And then we have set B. Set B has 1 and 2. And then we have set what? 0, 1, 2, which is set C. So we can have a path from here to here, right? We can have a path from here to here and from here to here. In other words, 0, 1, 0, or we can have 0, 1, 1, or we can have what? 0, 1, 2. That's one way. Or we can have a path from here to there, here to there, here to there, right? Maybe 0, 2, 0, and then 0, 2, 1, and 0, 2, 2, for example. And then we do the same thing for this element. So basically, right here, this is all possibilities that you can have. 0, 1, 0, 0, 1, 1, 0, 1, 2, 1, 1, 0, 1, 1, 1, 1, 1, 2, okay? Or 0, 2, 0, and so on. Well, what does this mean? This means, for example, if I say A is a set that consists of all x from domain D, okay, for which Px is true. Px is a propositional function. It's very simple. Look here. Truth set. This is called truth set. Okay, a truth set, Px, truth set is denoted by this, all possible elements in a domain for which Px is true. And let's see this simple example. For example, I say A is equal to, let's see, okay. It says all integers, so our domain is integers such that x is equal to 1. So basically, this is A, okay? What is the truth set? What is the truth set of A, okay? Truth set of A, well, as you know, -1, absolute value is 1, 1, absolute value is 1. So there are only two integers that satisfy this condition, right? So the truth set of this proposition, or truth set of A, but we say the truth set of this proposition is basically -1 and 1 in this case, okay? Very simple. We will have 4 operations: union, intersection, complement, and difference. Union, if you have two sets, A union B is the set that consists of all elements that belongs to A and that also belongs to B, okay? So basically, if this is set A, if this is set B, okay, all elements that belongs either to A or B or both, okay? For example, here, this is A, which has 1, which has 2, and which has 3, right? But 3 also belongs to what? B. This is A, let's say, and this is 4, and this is 5, and this is B. Okay, so this is A union B. That means A union B will be 1, 2, 3, 4, 5. Okay, all elements that belongs either to A or B or both. Okay. And how many elements? What's the cardinality of the union of two sets? And let's get back to this example here. Assume that I have A, which is 1, 2, 3, and I have B, which is, this time I'm going to make it 3, 4, 5, 6, let's say, okay? What is the cardinality of A? Cardinality of A is what? 3. What is the cardinality of B? Which is 4. What is the cardinality of A intersection B? What is A intersection B? A intersection B, I will show you in a minute, the elements that belongs to A and B. You see, for example, here 3 belongs to A and 3 belongs to what? B. Therefore, there's only one element, which is 1. And cardinality will be that elements that only belongs to A. Elements that only belongs to A, and the elements that only belongs to B, and the elements that belongs to A and B, right there, right? So here, A has 3 elements, B has 4 elements, and common has 1. But this 1 is counted twice because this element belongs to A, this element belongs to B. If I say 3, 4, 7, this 3 includes 1, and this 4 also includes 1. So I need to subtract that 1 from there. So the cardinality will be the cardinality of A cardinality of A, cardinality of B minus the cardinality of A intersection B, which is right here. I mean, intersection is obviously, you know, if you have two sets, A and B, intersection is all elements that belongs to A and belongs to what? B. And if there is no intersection, for example, if this is A, this is B, if there is no intersection, we call A and B are what? Here, disjoint, okay? If the intersection is empty. So what's the intersection of 1, 2, 3, and 3, 4, 5? As you see, 3 belongs to A and 3 belongs to what? B. So intersection is simply what? 3, the set 3. Okay, what is the intersection of these two, 1, 2, 3, 4, 5, 6? That is obviously what? Empty set, because there are no elements that belongs to both A and B. Complement, well, this is the universal set. This is A, right? Complement is all of the elements in the universal set that does not belong to A, okay? For example, if you recall, we had this universal set. This was all letters in the alphabet. And then we had set of vowels, right? And then if this is the set of vowels, A, E, I, O, and U, which is 5 of them, the remaining 21 letters, is what? Basically complement of what? V, okay? And sometimes either we denote it like this, or we can say A to the power C, complement, okay? All right, what is if U is positive integers? In other words, if our universal set is positive integers, which means Z plus, okay? Positive integers less than 100, sorry. So universal set U, basically here is 1, 2, 3, all the way what? 99. Okay, so what is the complement of? The question is, what's the complement of x? X bigger than 70. Well, the complement will be what? All the numbers in U, which is not bigger than 70. So all the numbers between 1 and 69, with all the numbers from 1 to 69, including 69. Okay. Sorry, this was bigger, so less than or equal to 70. So basically, okay, here, what is this? This is 71, 72, all the way to what? 99. Our universal set was what? 1, 2, all the way to 99. Therefore, the complement of this will be anything that doesn't belong to this set, which is from 1, 2, all the way to what? 70, including 70. And difference set, this is very easy. The difference between A and B, okay, let's A and B set. The difference of A and B is denoted by A minus B. This is the set that contains all elements of A that only belongs to A, that does not share anything with B. Okay, so this is A difference B. Okay, how about B difference A? Obviously, B difference A will be what? Right here. This is B minus A. That means all the elements of B that only belongs to B, that does not belong to A. Okay. So if you look at this, what is this? Well, it's pretty simple. Look here. What is B naught? B naught. B naught consists of all elements which are not in B. That means everything in the universal set that doesn't belong to B is basically what? B naught. So this is B naught. What is A intersection B naught? Isn't that the blue area right here? So basically A minus B is equivalent to what? A intersection B naught. Similarly, B minus A is equal to what? A naught intersection B, okay? Okay, so now we have 3 sets and we are asked to find A intersection B minus C. This is pretty simple. We have our universal set, U. In the universal set, we have A, we have B, and we have C, right? This is A, this is B, this is C. First, I'm going to take care of B minus C. That means all the elements that belongs to B but does not belong to C. Isn't it this? All the elements that belongs to B right there, but that does not belong to C, right? So this is basically here is B minus C. Then I will take intersection with A. Well, and we know that this is A right there, right? So intersection will be what? This area right there. So right here is what? A intersect B minus C. How about this one? This is pretty easy too. We have A, we have A, B, and C. Now A intersection B, okay? Let's show it here. We have A, we have B, we have C. So A intersection B, this is A, this is B, this is C. It is right there, right? A intersection B. What is A intersection C? A intersection C is what? This one. And it says what? Union of it. Since it is union, so it will be basically here, here, everything. Here is what? A intersection B and A intersection C, and then union of it. Okay, and the last example, this is also pretty simple. We have A, we have B, and we have C. A, B, C. It says A intersection B naught, right? A intersection B naught. Well, remember this is A minus B, right? This is A minus B. So it's gonna be everything that is in A but not in B. So isn't it this guy? And this one is what? A minus C. It's in A but not in C, okay? So here that will be in A but not in C. Isn't it this area, right? And it's looking for union of it. So union, that means this one, union this one. So everything right there is the union, okay? Set identities. Set identities are extremely important. All right, the first set identity is the intersection of A with universal set is itself. That's very clear, right? We are going to prove those, but if this is the universal set, and if this is A intersection U is obviously A. How about A union empty set? If you add empty set to anything, empty set does not contain any elements. Therefore, it's going to be the same as what? A. And domination laws, well, A union U will be what? Obviously, A union U must be what? U. How about A intersection empty set? That's empty set because empty set doesn't have any elements. So if you intersect with A intersect empty set means all the elements that belongs to A and that belongs to empty set. Since empty set does not have any elements, its intersection must be what? Empty set. How about A union A? Well, A union A is obviously A. A intersection A is obviously what? A. That's called idempotent laws. And the complement of complement is itself. Why? I mean, this is also pretty simple. If this is A, the complement of A is here. Okay, and the complement of purple is what? A itself. So the complement of complement is the set itself. Okay. A union B is equal to B union A, or A intersection B is the same as B intersection A. We are going to prove those. Well, this is associative law. A union B union C, doesn't matter where you put the parentheses, or A intersection B intersection C, doesn't matter where you put the parentheses. But this distributive law is important and we will prove it. A union B intersection C is the same as first A union B. It's like distributing A union B and then A union C and then intersect. Similarly, A intersect B, A intersect C, and then union. That's the distributive law. okay? And this is important. This is very similar to propositional logic. De Morgan's law tells us that A intersection, the inverse of A intersection B, okay, is inverse of A, inverse of B, or complement of A, sorry, complement of A intersection B is the complement of A, complement of B, and then combine them with union. And similarly like that. If, of course, if we have multiple sets like this, and if we want to get the complement, it's going to be A1, A2 complement all the way to what? AN complement, okay? Okay, absorption law. Well, this tells us, look here, we can prove in different ways. This one tells us first do that and then do that. A union A intersection A union B. That means A intersection A union B. Okay. Well, A union B is obviously bigger than A. And if you intersect with A, it should be A. We will prove those, but just intuitively, that should be true, right? For example, here, if we look here, what does it tell us? A intersection A union B. I will do that. A intersection A, then union A intersection B. A intersection A is what? A union A intersection B. A intersection B is obviously is a subset of A. Therefore, this union must be what? A. And well, A and complement of A, if this is U, if this is A, this is U, this is A, complement of A is what? Here. And this is A. Therefore, A union complement of A will be what? Universal set. And A intersection A complement is obviously empty set because they don't have any common elements. Okay. So how do we prove those identities? Well, there are different ways. We can use 3 different ways to prove the set identities. One is that we will prove that each set or each side of the identity is a subset of the other, or we are going to use set builder notation or membership table. So let's see each one with an example. Let's prove that A intersection B is the same as, complement of A intersection B is the same as the union of A complement and B complement. Well, how can we show this? This is very easy. We are going to first show that A intersection B is a subset of A complement, B complement. So what does this tells me? It tells me that this set includes this set. Similarly, if I show the opposite side, if I show that A, B, so that means if I show that this guy is a subset of this guy, so this implies that both of them must be equal. For example, X equal to Y. How do you show that? If you show that X is a subset of Y and Y is a subset of X, this implies that X must be the same as Y. We are using that logic right there. So we need to show that this is the case, and we need to show this is the case. What does this mean? This means I will start with an element that belongs to what? A intersection B naught. If I show that any element that belongs to intersection B also belongs to, any element that belongs to the complement of A intersection B, if it is also an element of the union of A complement and B complement, then we prove the first part. In fact, here it is. Let's start with an X that belongs to what? A intersect B complement. That means if X is an element of this, that means X is not an element of A complement, A intersect B, right? So in other words, X is not in A and X is not in B. Well, the inverse, what do? We get, remember, so basically it's proposition, right? If you have two propositions, P and Q, how do you get the inverse of it? P inverse or Q inverse, right? So that's what I'm using here. I get the X belongs to A is a proposition, X belongs to B is another proposition with AND, and I get the inverse of this, or negation of this, and then AND becomes OR. That means X is not an element of A, and X is not an element of B. In other words, X is an element of A complement and X an element of B complement. In other words, X an element of A complement or, union B complement. So we started with this and we show that this is the case. That tells us that this guy is a subset of this guy. Now I'm going to start with the opposite. This time I'm going to show that this guy is a subset of this guy. Therefore, I will assume X belongs to the first set here. In other words, X is an element of A complement union B complement. That means X is an element of A complement or X is an element of B complement. That means X is not an element of A, or X is, no, there is something, okay, here, or X is, X, here, X is not element of A, or X, the same thing, actually, we should do that right here, right there. X is not an element of B. In that case, I will say X is not an element of A, or X is not an element, X is an element of A, or X is an element, it is negation of X an element of A, and it's negation of X element of B. And if you go here and get the bigger parentheses, and or becomes and obviously we get that result. So that's trivial. So we've also proved this side. Therefore, we conclude that those two identities are the same. Another way, let's, instead of, well, maybe this was too complex, prove that one is a subset of another and so on. Instead, I like this one much better. We do directly use we use the propositional logic directly, and we prove it. For example, here A intersect B complement means all X such that X is not in A intersect B. That means all X such that I use the propositional logic, X in A intersect B is not true. That means X in A and X in B is not true. That means X in A is not true, or X in B is not true. In other words, X is not in A or X is not in B, right? That means X is in A complement or X is in B complement. In other words, X is in A complement or B complement. And basically this set is exactly this set, right? So we just prove directly, okay? Or we can use membership tables. For example, it might be easier to use membership table to prove this identity. This is very similar to propositional logic, true and falses. Think about set A, B, C, okay? And we are gonna list all possibilities. For example, an element may belong to A, B, and C. An element may belong to both or three of those sets, or an element may belong to only A and B, but not C. An element may belong to A and C, but not B, and so on. Since we have three sets, there are 8 possibilities. Why? 2 to 3 is 8. That means we can have an element that belongs to all of the sets, or an element does not belong any of the sets, and anything between, okay? So now let's think about this, B union C. What is B? Well, actually, we are not proving this. We are proving this identity here. This is not the example, okay? A intersect B union C is equal to A intersect B union A intersect C. That truth table, I think I made a mistake. Instead of providing the truth table of this, I provided the truth table of this. So let's focus on this, okay? So what is B union C? Well, if an element belongs to B and C, that means it belongs to B union C, right? If an element belongs to B but not C, still it belongs to the union. It doesn't belong to B, but it belongs to C, still it belongs to union. If it doesn't belong to any one of them, it does not belong to union, right? Similarly, so 1, 1, 1, 0, 1, 1, 1, and the last one will be 0 because it doesn't belong to B, it doesn't belong to C, so this is 0. Then I have B union C and A. So I'm going to look at this column and this column. So if an element belongs to A and if an element belongs to B union C, it also belongs to the intersection. So 1 and 1 is 1. 1 and 1 is 1. 1 and 1 is 1. 1 and 0 is 0. 0 and 1 is 0. 0 and 1 is 0. 0 and 1 is 0. 0 and 0 is 0. So this is what it is. Similarly, I'm going to go and do A intersection B. 1 and 1 is 1. 1 and 1 is 1. 1 and 0 is 0, and so on. A intersection C, 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 0, and so on. Then I get the union. You see, this guy, union this guy. That means this guy, this guy. 1 or 1 is 1, 1 or 0 is 1, 0 or 1 is 1, and so on. And if you look at this column right there and this column right there, you can tell or conclude that this guy and this guy are the same. Okay, so this was a very simple class or lecture, and I hope you enjoyed it. But still, we have to formalize the language, even though it is simple. Next lecture, we'll talk about functions.